So one of the things I wanted to show you is just go back over various ideas from the course with a little bit of a focus on plotting, a little bit of a focus on dealing with the vectors in Mathematica. So some of these we've seen in group problems, we've seen in other places. Kind of want to do it over. I can't remember if I use any of the Mathematica handbook tools, but I do when I'm doing the vector calculus. I tend to load the deform thing if I need it, because that's if it has a bunch of the functions that Peter Taborek wrote that make derivatives nice and things like that. The first thing I want to do is return to this curve I gave as an example, which was sine 2t, cosine 2t. And when you're dealing with parametric curves, it's very useful to do parametric plot. It's very useful to get a good idea of where you're doing it. So notice this is the plot from 0 to 3/4 pi for t. And I get the sense that the curve goes from there from 1 to -1. If you remember, we were integrating from -1 to 1. So I could just do from 3/4 pi to 0, going back the other way. Now, what was interesting, of course, is I hadn't specified where you're going. And so some people did, what is it? I think if I do minus pi over 4 to 0, you get the other piece of the curve. And that's perfectly fine in the context where I did it, because I didn't tell you which one to do. I would have to specify it. Now, turns out that due to a symmetry, these two quadrants cancel, and you get the same answer, whichever one you do. But let's go back to the 0 to 3/4 pi. The other thing to be aware of is I am adding plot style here, something I haven't talked a lot about. Most of the plotting functions use plot style to do things like change the color and to make it thicker. And you have two options. You can use the built-in red, blue, green, yellow, black, and you can use built-in thin, thick. There's a couple of other ones to get thicknesses. You can also do it specifically by point size and by inch and other factors. So there's a lot of control you can get over Mathematica and the plots. And you can do the labels, and you can control where the origin is. So you really can make your plots look publication grade. And a lot of people use Mathematica to make the plots for their figures. I find it's a lot of typing and commands. And for me, if I'm going to make plots that I'm going to publish, I tend to use other software like Origin. I hate Excel. I don't think anyone really uses Excel to make plots for publication. They just never look quite right. But Mathematica, if you get good at the commands, makes very nice ones. And one of the advantages, as was just asked during the break, is I can pull up the graphics tools. And it really is almost a drawing program now. And so I can, if I want to highlight this region here, I can draw a square there. And then I can start doing other stuff with my square using all the various tools. I can make it thicker and opaque and rotate and draw other squiggly things. And I can add text. And so you can really build up, quite interesting plots and drawings when you use the drawing tools. Now, the next thing we can do is add in our vector field. This was the one we had in class. And one thing to learn about that I didn't mention is sometimes it's helpful. This is most helpful when your vector field diverges somewhere. Mathematica doesn't like to plot things with divergences, and particularly when you're doing things like if you're doing things in 1D, you just change your plot range. And it's usually pretty easy. In 2 and 3D, what you want, the easiest way to do it is with this thing called a region function. Now you have to use the Mathematica syntax of a function We haven't dealt with that very much, but what you do is you tell it what the variables are. In this case, it's x and y, and then you tell it what its function is. And in this case, I want everything outside the circle of radius 1. So I can now see my vector field a little bit better. I'm not distracted by what's in the middle. I see it coming in. I see it going out. And so now, when I put this together with my plot, it's a little easier to pick out what's happening at the surface. So if I want to think about what this integral really means, remember I'm doing the integral of f dot dr. So I've got my little dr's along here, and here's my f's dotting it. And that will let me know what's going on. So I definitely need, it's a good thing I have some places where it looks like things are going parallel. If everything was perpendicular, my integral would come up to 0. And I definitely see, it looks like what comes in here goes out here. And that's that symmetry that I'm getting. Now, one thing I did not show yet is an alternative view of plotting this is with the stream plot. And it just depends what you're going for. So notice with stream plot, what I'm basically plotting here are the electric field lines, the stream lines. I'm connecting my vector field up. So when you do that, it's a lot harder to get an idea for the magnitude. Now the streamlines, depending on how you set your settings, the closer together you have streamlines, usually the bigger the field. So that's a general rule of thumb. Now, but notice it does give you a much better idea of the direction, because you've got that continuous line. And you can plot it with and without the arrows if you find the arrows distracting and things like that. Now with stream plot, do I do it here? No, I talk about it later. Okay, let's just put them on together. So notice by having the full lines, it is a little bit easier to see how they actually cross. And I could get really fancy. I could compute the normal to this curve, and I could plot those normal vectors, and then I could see the angles right where they hit to get an idea of what's going on there. Now, this vector field, if I give it a name, if you remember we went through this in class, does not have a non-zero curl. Its curl is minus 2y. So in principle, the integral around a closed curve is not always 0. Now, the particular one centered on 0 has an accidental symmetry, we call it. It does turn out to be 0. But I can take my circle and I move it off by 2. And now if you've noticed, I've changed my notation a little bit. I'm actually using the normal parameterization for a circle. Cosine t, sine t. Right? X equals cosine t, y equals sine t. I've just shifted the center to 2, 2. So I've just taken a unit circle, moved it off center. If I look at the streamlines off center, I can plot them together. And it's still a little subtle, right? It's not real clear whether this should be 0 or non-zero. But we know that the curl inside of here is non-zero. See, with the other case, if I look at it, knowing that this is the curl, minus 2y, can you tell me why you would expect that integral over a circle centered at the 0, centered at the origin, to come out to be 0? What? No. I've got a full circle. Think about this, right? I just said, so I have a circle centered on the origin, and the curl of my vector field is minus 2y. So when I integrate around this closed circle of v dot dr, why do I not get 0? I mean, why do I get 0? Sorry. Because I'm going to be adding up equal amounts of positive and negative y, right? I know already that that's minus 2y. And so as soon as I put my circle in this quadrant, why do I know now that that's not equal to 0? Because what values of y do I have?
0 and positive.
Only positive ones. So do I expect that integral to be positive or negative? Negative, because my curl is minus 2y. So using facts about the integral over the area are going to help me. So if I go through, dun, 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 dun. Now let's look at some detailed Mathematica tricks. I didn't want to actually sit down and do any of the figuring out the line integral by hand per se. What do I need to know? Well, I'm going to do f dot dx. So I need my ds vector. Well, ds is just dx and dy, which is just the derivative of cosine t dt and the derivative of sine t dt. So I can just use that to actually compute my ds. If I wanted to, I could have typed it in. I could have just said ds is minus sine t and cosine t. And now I'm going to take the vector field dotted into that. Now, what do I have left that I have to do? I can integrate this, and this is effectively a dt, and this is a dt, because I've had that parameterized. But what do I have to now do with this? If I'm integrating over t, what do I have to do? I have to change the x and y's. And how do I do that in Mathematica? I just substitute in for what x and y is. And that's the beauty of the slash dot rule. And so now I separated it out for you. I could have done, and I did, I put it in here. I can do this as one step. There's my v dot ds, and there's my substitution, and then my integral from t equals 0 to 2 pi. Yes?
If you did that substitution after the integrate brackets, that would fail miserably. Yeah.
Because it doesn't know how to integrate with x and y.
So the syntax has got to be all.
Yeah. Because that's not what you're doing. So keep in mind, let's just write it out for you so you can see what we did. If I have the integral that's the integral I wanted to do. And I had my curve that I'm integrating it over, parameterized by x equals cosine t, y equals sine t, in this case plus 2 to shift it. Okay. Then ds, which equals dx I hat plus dy j hat, is equal to minus sine t dt, that's the dx, so notice to get dx, I take dx dt, and then plus the cosine t dt. So that's the I hat, that's the j hat. So then when I do the dot product, this piece goes there, this piece goes there, and I've turned my integral to 1 over t, and so now I need to plug in that for x and that for y. about the messiest slide I could possibly make. Right? That's what I'm doing by hand. That set of operations, which is what we practiced earlier in class, is exactly this set of Mathematica operations. Compute ds, do the vector field dotted into ds, and substitute in for x and y before you integrate over t. So notice in this case, if you understand the procedure and you have some really complicated arbitrary parametrization of x and y in terms of t, it's still these three steps. All you've got to do is take the derivative of x and y with respect to t. That's your ds. Then dot it into vector field, and then do your substitution and integrate. So this is a case where Mathematica really makes it a lot easier when you understand what the process is. So I think this is an important example now. Now that we've done a lot of it and you've had time to sit with it and have done it by hand and everything, go back and see the power of the Mathematica /dot. That's one of the really cool things about the symbolic manipulation. The fact that we can just keep things as vectors and do the dot product between the ds and the vector field. So there's a lot here that's compact but very powerful. Now, if you recall, to make it 0 curl, we just have to change the one coefficient. The 3 becomes a 2, and now the curl is 0. And it's really interesting to look at it. I hope no one's red-green colorblind. But the first thing I do, or blue-green colorblind, there's the difference between the two fields. I think this is absolutely amazing. One of these has 0 curl, and one of these doesn't. Which goes to show that our intuition for when the curl is 0 is not always that great. You know, some things are obvious, but some of these can be quite subtle, I think. I don't know, maybe somebody who's done a lot of these can look at it and say, you know, the green lines have 0 curl, and the blue lines don't. But I challenge you to make that decision. Now, it has, of course, a dramatic effect. Well, first of all, I can plot the same plot here and look to see, and you know, again, it's not going to be real obvious what you've changed about going around this circle. But sure enough, since the curl is 0, when I integrate my vector field dot my ds, I haven't changed ds, and I do my substitution, I get 0, as it has to be, because the curl inside is 0. So it's a pretty cool situation. Any questions on that one? I think that's a really powerful example, both to see the power of what you can do in Mathematica, if you can get down this idea of what it means to use /dot. /dot is a key concept to have. Switching gears slightly, I just wanted to show you a 3D plotting example. And again, this comes down to using /dot. So the theme for this Mathematica file is really /dot. A couple of things that are useful. If you've forgotten your coordinate transformations, Mathematica can nicely do this for you. So here I'm going spherical to Cartesian in terms of r theta phi. And this is Cartesian to spherical. And so this is r theta and phi in terms of the Cartesian. This is x, y, z in terms of the spherical. It's a little weird, right? This is like Cartesian to spherical. This is plugging the Cartesian into the spherical. So the arrow I find strange. That's just me. But it might make sense to you. But you can see what you get out of it. Now, if I want to use this cool vector plot stuff, one of the few drawbacks of Mathematica is that at the end of the day, I can only vector plot Cartesian vector fields. And a lot of vector fields we're given are in spherical or cylindrical. So let's plot the vector field of a point charge. I know it in basically spherical coordinates. It's 1 over r squared r hat. So what I need to know is what is r hat, r theta, r hat, theta hat, phi hat. And to get there, I can first write them easily. This is a weird thing, so let's look at this notation carefully, and you got to pay close attention. This is the basis vectors in the x, y, z components of them as a function of r theta phi. Right, so the easiest way to write them, and this is just your trig. You can see it if you look at r hat and theta hat. You know, they have a cosine theta minus sine theta part. That's the obvious projection. Whereas phi hat doesn't worry about a z component. Phi is in the plane, right? So phi is always pointing with x, y. So phi is the easy one. It's the original polar one, okay? It's a little weird because of the way we go counterclockwise, as a minus sine phi cosine phi tells you the vector where it's pointing. But what we really want is we really want these as a function of x, y, z. So we're going to get there. Our vector field, q over r squared, in Cartesian components then, is all we got to do is write, this is the vector that's telling us the Cartesian components. So now we have our E field. This is the x hat, y hat, z hat component of our E field. But it's now still as a function of theta, phi, and r. So what I do is I slash dot my r theta phi conversion into x, y, z, which I got from up above. So that's my r vector conversion. I now use my slash dot, and now I have my electric field in x, y, z components as a function of x, y, and z. And notice all those ugly arctans and everything and sines and cosines, Mathematica did it. It took care of it nicely for me. If you go back and look in a textbook, you see that this is what you get. X is over things, y over 3/2, z over 3/2. So it may look familiar to you. And now what I can do is I have to give the charge a value, and I have to eliminate the center. Oops. No, it worked, yeah. And now I can plot my field in 3D. And the reason I eliminate the center is why? What happens to the electric field at the center? It diverges. 1 over 0 diverges, so that's a bad thing. So this is hard to, I mean, I hate picturing 3D, but this is better 3D than not using 3D plotting. So now I can make 3D vector fields, but you do have to go through, if it's not in Cartesian to begin with, you have to convert to Cartesian. And there's two pieces to it. There's getting the basis vectors, which is easiest to do as a function of the original coordinates, and then converting those to the XYZ coordinates. So there's really two steps. You've got to get into XYZ components. So this one is kind of slightly advanced Mathematica because of that double conversion, but it's important. It's not a bad way to learn to think about these things. So I encourage you to play with 3D plotting. I'm going to try, I'll send an email, but on Thursday, bring your Mathematica, bring your laptops, because I'll try and have one where you can practice some of this 3D plotting. And we're done.